Alright, let's look at a different exponential function. This exponential function has the variable x in the exponent. That's basically the definition of an exponential function. The base this time is 1/2. If the base that we see is in between 0 and 1, then the graph is going to look a little bit different. You notice that we still have a similar shape, but it actually decreases, or it's bigger on the left, taller on the left, and as you move from left to right, the graph looks like it gets lower and lower. That's what's going to happen to the graph if your base is in between 0 and 1. So let's just see what happens here. When we go to graph it, we have a little t-chart here again. We have some x values that we want to plug in. The base, every single time I plug in one of these x values, the base is going to be 1/2 every single time. So the base is not going to change for the exponential function. What does change, or what varies this time, is going to be what we put in place of x. And that x is now in the exponent. So when we put x is equal to 3 into the function, we get an exponent of 3. And then when we put an x value of 2 into the function, we get an x value of 2. We get that exponent of 2 and 1 and 0. So all of these numbers become the exponent on that base. So an x value that goes in becomes an exponent. So let's see what results that we get out. If I do 1/2, remember that's 1/2 times itself 3 times. We multiply across the top, I get 1 times 1 times 1, which is 1. 2 times 2 times 2, which is 8. So we end up getting 3,1/8. Okay, and that point gets plotted actually down here, an x value of 3 and a y value of about 1/8. And we have an arrow here. I'm just going to go ahead and put that down there since we're here, but our graph goes forever to the right. And we notice again, it kind of looks like it's hovering right above the x-axis. Okay, what happens when I put an x value of 2? I get 1/2 squared, so that means 1/2 times itself twice. 1/2 times 1/2, we get 1 times 1 across the top, I get 1. 2 times 2 is 4. So we get 2,1/4. Now remember, we also have that shortcut. We could just cube the top of the fraction. 1 cubed is 1. We could cube the bottom of the fraction. 2 cubed is 8. So you can do it the long way or the shortcut way that we've talked about in the past. Alright, 1/2 to the power of 1. Well, that's just one of those, so that's 1/2. That's all we've got. So 1,1/2. Okay, see if we remember. We have a base of 1/2 raised to the 0 power. What is our rule for having a 0 exponent? Well, we said the base raised to the 0 exponent is going to be always exactly 1. It doesn't matter what the base is. So exponent of 0 goes in place of x, a y value of 1 comes out. So we have some points we can start plotting here. We got 0, 1. We have 1, 1/2, 2, 1/4. So it's kind of, this graph is actually kind of doing the opposite of what the last graph looked like, what the last graph did. Alright, let's go into the negatives. So we have to remember our negative exponent rule. Our negative exponent rule says if you have a negative exponent, that you're not going to work with the base you see. You're going to flip that base upside down. So instead of working with 1/2, we're going to work with 2/1. We're going to work with the reciprocal of the base raised to the positive power. So that's 2/1 raised to the positive 1 power. Well, that's 2 to the power 1, that's just 2. So -1, 2. And that point's here, -1, 2. We get that there. Alright, we put in a -2. That's really going to be flip that base 2/1 raised to the positive 2 power. That really is 2 to the positive 2 power, which gives us 4. So negative 2 goes in, 4 comes out. We can plot that point right here. And then lastly, 1/2 to the power of negative 3. Since we have a negative exponent, before we do anything else, we're going to flip the base, flip that fraction around, work with the reciprocal, raise that to the positive exponent. 2 over 1 is really just 2. Raising that to the power of 3, we get 8. So negative 3 comma 8. We're going to plot that point right up here. Now officially again, there's an arrow that points up. We could have chosen to continue with negative 4, negative 5, negative 6. We can choose any x values that we want to. I just chose 7 so we can look at the basic idea of the graph, but officially we could keep going to the left and to the right with this graph. Alright, so let's look at our domain and range again. Okay. Our domain, all real numbers. Every exponential function always has a domain of all real numbers. So always for all exponential functions. Alright, for the type that we're considering here, the range would be from 0 to infinity, but not including 0. Okay. So when you look at the graph here, you see when we look at the bottom of the graph never goes below the x-axis. The graph actually never even crosses or touches the x-axis, it just hovers above. So the y values that come out as a result never achieve 0 or anything less than 0. So 0, not including 0, to positive infinity is our range from bottom to top. Alright, horizontal asymptote, well, it's going to be the x-axis again, just like it was before. That line y equals 0. So right here, if I was to draw a dotted horizontal line here, the graph gets really close to that line. Just like it did with rational functions, we get really, really close, but we never actually cross that line y equals 0, or that's the same thing as the x-axis. Okay, is this a one-to-one function? That's our next question. Well, does it pass the horizontal line test? So every horizontal line that I could imagine drawing looks like it's going to cross through the graph only one time. Even when we get down here, it only crosses one time. So is it a one-to-one function? The answer is yes. It passes the horizontal line test. If it passes the horizontal line test, what does that mean? That means that it has an inverse function. The next graph that I want to look at is actually going to be really significant as we progress into the next section. It's something called the natural base. The natural base E, that's a letter that we use basically to represent a number, kind of like pi. So if you recall, you thought about pi before. Pi is approximately 3.14, and sometimes we stop there. But there's really an infinite number of values that come after the decimal place. But typically, we think about pi as just being about or approximately 3.14. Not exactly, but approximately, and that's usually good enough for what we're doing. We have another number, e. So one of the important parts here is that e is a number. E is not representing a variable. It is a number. We call that number the natural base because it pops up in a lot of scientific applications. So it naturally appears in the world. So we typically think about this number is approximately, we have some values. This actually is not all of the numbers that come after the decimal. This actually goes on forever. But we typically approximate it as about, rounding up to the nearest 2 decimal places, we think about E as being, about 2.72. Okay, we always write E, and then we can think 2.72 approximately. When we talk about pi, we write that Greek letter pi. So we write this, but we think 3.14. But remember, this is just an approximation. It's not exact. That's the same thing for E. This is what we call the approximation, whereas E represents the exact value with all the decimal places. Okay. The letter E, that base, is frequently used as the base of an exponential function. So the exponential function here, f of x equals e, remember that's about 2.72 raised to the power of x. So we're going to call this the natural exponential function. Alright. Now you will need a calculator to do these, and we're going to look at how to do that. First of all, we want to remember that the base is e, so we're going to write e. I'm going to use red here, so e, 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 all the way down. That's the base, it's not going to change. The exponent is what changes, so we'll put a 3, 2, 1, and so on. Now everything we see here would be considered to be the exact values, but we would like to come up with some approximations. Now there's a few of these we don't need approximations for. For example, e to the power of 0. We know e to the power of 0 is 1, because any base raised to the power of 0 is 1. E to the power of 1, we know that's exactly e, which is approximately about 2.72. We don't really need calculators for those two. Now the others, let's bust out a calculator. Now, you may not have a calculator at home. You can do it in your scientific calculator, but you can also use Desmos. And so I'm just going to show you in Desmos how to do this, and you're welcome to do this on a test or on homework. But Desmos is D-E-S-M-O-S, so Desmos.com. You can pull that up on your phone, on your computer. But once you get there, I'm going to click Start Graphing. Okay, and what you can do is you can go down here to this little keyboard, and you can type in E. Okay, and you can raise that to a power. So let's say I want to raise that to a power. You can use this little button right here, A with a B. That'll give you an exponent. Alright, let's put a 2 there. So it tells me that e to the power of 2 is approximately, or about, 7.38, and so on. Alright, so we can write that down in our notes. Let's round that. Let's say that's about 7.39. Okay. Now let's go e to the power of 3. So I'm just going to go ahead and change that exponent to be 3. That gives me about 20.09. Okay, so pretty good approximation there. Alright, now we have some negative exponents, and so let's put those in our calculator there. I'm just going to hit the back button. And I'm going to hit the delete button. And now let's do -1. So e to the -1 power is about, looks like about 0.37 if I round to the nearest 2 decimal places. Alright, let's do -2. I'm just going to hit the back button, hit the negative button, type in a 2. Looks like about 0.14. Getting pretty small here. Alright, let's go one more. Let's go e to the negative 3 power. Gonna hit the back button here, and then I'm gonna delete. Put a 3 there. Looks like we get about 0.05. So really small pretty quickly. Okay, it gets really small really quickly, but then it also gets really big really quickly. My exponent e to the power of 3 is about 20. That's pretty big, pretty quick. So let's plot some of these points. Let's do 0, 1 first. 0, 1 is here. And you'll notice that this particular point was on all 3 of our graphs that we looked at so far. Alright, 1, e, or 1, about 2.72 approximately. That's about, what's that about right here, right? X equals 1, the y value is just below 3. You can write 1, e, or 1, approximately 2.72. Alright, let's just plot one more. The rest of them are a little bit big. Let's plot e to the negative 1. Put an x value of negative 1 in. Our y value is about 0.37. Negative 1 about 0.37, about right there. Alright, this just gives us a basic idea of what this graph looks like. We have arrows on the left and the right, but that's our idea of our natural base e and how it works as an exponential function. A couple of questions. These should start feeling familiar. The domain. What x values are allowed to go into an exponential function to become exponents? All real numbers, from negative infinity to positive infinity. You can put in any x value that you want to as an exponent. But what comes out? Well, what comes out is always positive. So, and never 0. So we go from 0, not including 0, to positive infinity. So when we look at our graph again, we see that it looks like the graph is hovering right above that x-axis. So we have a y value of 0 as the horizontal asymptote. So the graph gets really, really close to the x-axis, but doesn't actually touch it or cross it. Is it a one-to-one function? Okay, well, let's go back and look. Is it one-to-one? To answer that question, we said look at the graph and does it pass the horizontal line test? And it does. Every horizontal line that I could possibly imagine drawing only crosses through the graph one time. So yes, passes horizontal line test. If it passes the horizontal line test and it's one-to-one, what does that mean? That means it has an inverse function. Okay, and the next set of videos is going to talk about that inverse function. That inverse function is called a logarithm. So a logarithm. Alright. The last page of your notes is just a summary talking about ideas that you would see for any exponential function. Talks about the domain, the range, some key points that you'll see on the graph. I'm going to let you read through that. Okay, we basically have said all of these things already in the video, but here's kind of all the things that we said basically all in one place.